Good afternoon. My name is Randall Nichols. I'm professor of practice at Kansas State University and director of their Unmanned Aircraft Systems Cybersecurity program. The books you see here have been written by my Dragon team, and 4 of them are available to you. They've been published within 2018 right up to 2021. They're published by the New Prairie Press website, newprairiepress.org/ebooks, and then you just put in the numbers 27, 31, 35, and 38. The textbooks are free, and we hope you'll enjoy our work. It's got years of research in it, and furthermore, pass it on if you like. Today's agenda is what we're going to talk about: unmanned aircraft systems in the sphere of terror and cybersecurity and cyber terror. And we're going to think in terms of the attack vectors and what advantages. We're going to think in terms of risk. We're going to look at the threats. Also, we want to talk about the cyber terror problem in terms of communication, separation, and navigation. And then how do we counter all this? Threats and countermeasures required. So why is there a UAS terror problem? Well, we have millions of small UAS and medium-sized UAS being purchased and manufactured all over the globe. And these advanced small drones carry all kinds of sophisticated imaging equipment, significant and deadly payloads. Low amount of training, very little certification required. Counter-drone systems are expensive and require a great amount of testing. Small drone manufacturing the cost is quite low, and it's going lower. It's a quick developing technology. In fact, it's way beyond the legal aspects. Within a few years, hobby drone tech has just developed into a variety of swarming suicide drones with ranges of 7 km and payloads of 40 kg. It's easy to weaponize. So what do the terrorists use it for? I want you to recognize that the problem we're going to be talking about shortly here is localization, is position fix. Recognizing the GPS and ADS-B systems are fundamental to the terrorist operations using unmanned aircraft systems. They use it for weapons, as a weapons platform, as a martyrdom unit, as a drone attack squadron. This is actually not new. They've had one for about 7 years, but now they have our equipment, or they have American equipment. Attacks using unmanned underwater vehicles are now being seen in the South China Seas. So continuing on the why, there's an attractiveness of UAS versus the cruise missiles to an adversary. Why? Because they can get over the perimeter defenses, the national borders, they can simultaneously attack, they can conduct an entire campaign, and the targets with unconventional weapons. Contemplate for just a moment the risk of a terrorist spoofing signals, giving false signals, to friendly forces, intelligence, and counter weapons assets. Here you're looking at the Shadow. It's a surveillance and ISR drone. This picture was taken in 2013 in the Logar province of Afghanistan at Forward Operating Base Stark. The Taliban now has several of these, and they're re-engineering them. Here you have the Scan Eagle, which is one of our favorites. The U.S. Air Force and Army use this a lot. They have 7 of them, I understand now, that were left right outside Bagram or available through Bagram, and these are about 7.5 pounds of payload. They travel anywhere between 80 and 100 knots, and it has a 11-foot wingspan. 7 of these are now in basically enemy hands, terrorist hands. Well, when we want to look at things, you need to do a risk assessment. You need to think in terms of risk, and there are several risk equations out there by some very prominent authors and agencies and so on. In my classes, I teach about 6 of them. However, this one is a qualitative one that my partners, Dr. Dan Ryan, Dr. Julie Ryan, and myself created about 25 years ago, and it's been in use for a long time. It's very straightforward. Basically, it says threats times vulnerabilities times impact divided by countermeasures is equal to the risk. We can quantify by using qualitative means or ranges. We can develop a range for each one of these things in terms of percentages, and recognize that if vulnerabilities are always going to be part of the system and impact is basically an accounting number, we can reduce this to at time state equals 0. Risk is a function of threats divided by countermeasures. When the threats go up, the risk goes up. When the countermeasures go up, the risk goes down. It's pretty much straightforward in that term qualitatively. And we use this especially in things like cancer studies for the normal case, the best case, and the worst case analysis. So let's talk about why there is a UAS problem. What is the threat, basically? Well, the threat is the risk of a successful terrorist attack on air defense systems via UAS and small UAS. It's higher, it's improving, and it's based because the commercial capabilities and accessibility are better. So advanced small drones capable of carrying sophisticated imaging equipment, significant deadly payloads are readily available to people on the civilian market. Who? Well, the range is wide. Terrorists, insurgent, criminal, corporate, activists, threat groups, and so on. But right now we have a special concern for in 2021 to 2022 of the Indo-Pacific region and Afghanistan as a new terror hub. Well, let's move to the core of that. The risk of a successful terrorist attack on a GPS system or GNS system, the global system, or ADS-B, which is our collision avoidance system basically for broadcasting, is also higher for the same reasons. But in this case, everybody, including terrorists, the determination that needs to determine their navigation positions is critical to controlling all UAS operations, in fact, all aircraft operations, and also underwater. Therefore, it should be a priority in the national aircraft safety plans. And this includes such groups as LEO, military, and civilian. We're going to talk about spoofing. We're going to pass over jamming because jamming is an easy thing for when it comes to the solution I'm going to give you in a moment called ECD. Again, the range is fairly high, and the object is failure of mission, causing failure of mission. So what kind of vulnerabilities, what kind of tools are out there? Well, some of the attack tools you see over there, the Metasploit group is quite effective, the Paradrone one. They can be software or hardware based, and they can have auxiliary tools like Kali, Wireshark, and other things like MIM or Man in the Middle. I have a list in my office of about 1,000 tools, so this is just a scraping of the top. So the FAA classifies attacks on or causes of problems on ADS-B and GPS systems for dropouts, erroneous data, lost link, collision, mission corruption as natural, artificial but unintentional. The one I'm interested in is artificial, according to them, but intentionally caused, which involves cyber attacks and jamming. We have some corresponding mitigation strategies, hardware design, meaning the adaptability of adaptive, what's called antenna arrays, a signal tracking capability, which involves receivers, filtering, mitigation, single sourcing. Most solutions are single source for jamming. That's not the case for ECD. And again, ECD is a little later. Positioning, we have stochastic models based on jitter and changes in the signal. But cyber attacks on unmanned aircraft systems and GPS represent a much greater terrorist threat and safety issue than currently the FAA is approaching its understanding. They are looking into it, though. So UAS are just nothing but a SCADA machines. They're basically flying SCADA. SCADA systems are all over the world and act in the control of everything you know. Your cars, your refrigerators, your heating systems, our satellites, everything. Basically, they are control system, supervisor control system that takes in the data and tells it what to do. I mean, that's an easy way to look at it. And there are lots of interfaces to it. And some of the newest interfaces are called IoT. Typically, it includes such things as a master, a remote, and a communication links. These are all handled in terms of real-time monitoring and control. There are some inherent vulnerabilities, and they ease of operation outweighs security. There's a tendency that we don't want to worry about security. Let's take the ease of operations. Poor authentication. Remote access is allowed because nowadays nobody comes out to fix anything. They go to the internet. Weak access control lists. The firewalls are non-existent for all practical purpose. It's the first target of compromise of the attacker. It's a low-hanging fruit. Wireless technology is a monster when it comes to vulnerabilities. Public information is available on almost every system. The Iranian attack a few years back on their nuclear facilities was based on vulnerabilities that were not necessarily known at the time. They were called zero-day, a series of them. And once the SCADA system was recognized, it targeted the SCADA system and through these various vulnerabilities and other attack tools. So communication has its own software architecture. Processing is important. Latency is important. Processor clock speeds. These are all things that SCADA systems essentially put out there for the hacker to touch. Some of the common attack vectors on the SCADA systems on a UAS are misleading and manipulating the output data, especially to the actuators or reactors. One of the interesting things we can do is manipulate the alarm systems. We can manipulate the waypoints. We can manipulate the control systems. We can manipulate the battery levels, so on. We can change the history so you don't even know what happened. And then we can force a deadline miss on certain task actions. So for instance, the surveillance would be 5 minutes late. We can have attacks on software because of the privilege and buffer overflows and normal ones. We also have what's called a loss link protocol, which ensures the safe integration into the NAS, but it's basically the fail-safe. Well, fail-safe or not, the loss link protocol is part of the SCADA system and it can be hacked. And here's a little picture of that. We break the link, we break the direction, and we now have control of the UAS. Communications threats is another point. Corrupting the authentication of ground station communication is just as easy as anything else. Again, the attack frequency doesn't increase the probability of detection. Countermeasures can't be applied unless the target or attack method known. Spying can continue undetected, even with the hacking. Hijacking the UAS by hacking the ASIC chips. This was done over England a while back, where an ELINT plane, we found backdoors there. One of the problems with the ASIC chips, which are such a useful operation, useful chip basically, are the supply chain risks. We don't know where they're coming from. If you're not manufacturing them yourself, somebody can put in a back door. The trusted vendor operations are not trusted. We tend to take the cheapest wherever it comes from. And unfortunately, not everybody is honest about these things. We have no real checks on the supply chain that are effective. We used to, not anymore. We used to have about 80% of the market being America, and much of it went through outlets with national security agents or groups like that, or standards groups. Now this is not the case. We can spoof the ADS-B system, and we're going to talk a lot about that in a moment. But basically, it is a critical system for collision avoidance. It is for air traffic control. The messaging can be received, decoded, and resent and tuned. Aircraft position on tracks are simple to fabricate. They are not necessarily simple, and they're simple to detect, but there are some complex ones that aren't so simple. Some of the conventional vulnerabilities of air defense systems include the early detection or danger close thinking. And there we have restricting collateral damage by catching it in time. This is usually done by passive or active radar surveillance. The terrorists think in terms of why would they want to choose a UAS versus a missile, for instance, and Hamas. Hamas throws lots of missiles over there, and we over on Israel, and Israel knocks them down with the Golden Dome, with the dome. And you're like shooting a 22 bullet with a rocket. It's a very expensive process, but very effective. Well, UAS can come in lots, and the toughest organization are called swarms or teams. And against missiles, data fusion works better on larger targets, reactive for longer ranges, and it's suboptimal for close in and within a mile. So there's a small radar signature. It can be hardened. There are ways of protecting against this, but from the standpoint of vulnerabilities, it is quick, quiet, deadly, and noise detection is difficult at times, except in urban canyons. So some of the things we have seen on the military defense systems are backdoors and hard-coded passwords. We've seen the SCADA and the SATCOMs exploited. We've seen poor authentication system. We've seen games scheduling, which is controlling the takeoff and landing crews. We have seen fuzzing, digital update rate, control acquisition, buffer overflow, hardware directs. These are just some of the attacks that we have seen. Let's move now into a little bit more into what I call the GPS sphere, or the spoofing sphere. Navigation in 3D space is quite difficult. There's an awful lot of data. You not only need the 3 directions, you also need time, and you need the position in space with respect to where the satellites are with respect to the stars and so on. This involves quite a bit of data. And most of the research has gone to single source attacks. That means the transmitter is in a single source and going after a single receiver generally. And those can be detected and especially from the jamming standpoint, can be filtered out. But navigation requires an awful lot of decision making. First of all, detect, track, evaluate, prioritize, declare, determine, command, execute, repeat. These are the navigation loops for the sense and avoid systems. Well, how do they do this? Well, by vision, acoustic, infrared, LiDAR, passive, and radar. These are the primary ones. Attitude estimates, what are we estimating basically? And there we are, the rotation, the position, velocity, and altitude, the time. Time, by the way, is interesting because the clocks in the satellites are hugely, very, very, very specific, very accurate compared to the clocks in either the ground stations or the UAS. So precision clocks are important. Spoofing, what is it? I've talked about it a little bit. GPS spoofing is deliberate transmission of forged GPS signals resulting in the GPS receiver computing its location wrongly or failed to estimate any location at all. The worst case in a GPS failure, depending upon where it is, because everybody uses them, and vessels at sea or airplanes and so on, or UAS, is a complete failure of the mission. Now, the risk levels range from Part 107 tolerance. Risk at 107 is very, very low because it's a sterile environment, essentially. Everything is controlled. But near airports or out in a military zone or in the open sea, we now have things that are much more hazardous, almost catastrophic, especially at sea where a vessel can be harmed enough to potentially sink, as you'll see. And is it probable that this can happen? Of course it is. We've got years of experience saying it's probable. Is it probable in terms of the FAA's FAA standards? Yes. Does it range lower? Yes. It all depends on what the relationship is. What's the environment? If it's 107, it's the lowest. If it is BVLOS, you have another level up. Third level up, it'll be open or urban canyon. That's a completely different approach and more difficult at times. And then we have what I call the near airports. Spoofing techniques, there are actually 3 levels of classification. One is simplistic, which is just a COTS GPS simulator, an amplifier, and single antenna to broadcast signals toward the GPS classic receiver. It was expensive. It's not necessarily anymore because of software-defined radio. Simulator signals are not in the simplistic mode, are not synchronized with the available signal, and detection is easy. Intermediate involves the genuine GPS signal receipt, spoofing devices. These are, by the way, classic receivers. ECD, which we'll look into in just a moment, does not use a classic receiver. It uses what's called a snapshot receiver, whereas a classic receiver requires about 30 seconds of data. A snapshot requires 1 second of data. That's good news, but it's not necessarily enough always to give you the estimates you want. So several snapshots might be required. In the intermediate one, it's difficult to detect because you're using a fake signal that is broadcast relative to the genuine that is essentially the same, and you can prevent this using an IMU unit. The sophisticated spoofing attacks use multiple receiver and spoofer devices. Now we're attacking satellites, not one. We're attacking the group of satellites from sending false signals from multiple locations. And the angle of attack defense, which usually says where it's coming in from, and the calculation based on that, fails. It works for the simple and intermediate, but doesn't work for this one. And mitigation is usually by cryptographic authentication. It says, I got to check you. Who are you? The prior research on spoofing has excluded the fake signals. Most of the research I've seen over the years says we're not going to we're not going to include the fake signals. We're going to try to determine where they are and get rid of them. That's not the case in ECD. ECD includes the fake signal as a minimum on a minimum of 4 satellites, and then progressively and selectively eliminates their effect until the real weaker signals become apparent. Sensor spoofing causes confusion, overrides gains through hacking, causes denial of service. External references are more susceptible to jamming, spoofing than sensors with internal references. Jamming works for external, spoofing works for internal. Jamming during transmission interval, the adversary may reduce the rate of his transmission. Anyway, the enemy can allocate power across his subcarriers using an optimization algorithm. The simple spoofing case, again, the AIS receiver, automatic identification system spoofing is generation of false transmission masquerading as the correct encrypted precision signal, and then makes up the military version of the positioning basis or an unencrypted civilian acquisition code. It was chosen for its capabilities to recreate accidents using GPS coordinates, course, ground speed, and collision points. AIS is actually a 3 cyber attack 2 analysis, breaking the existing receiver locks, locking onto the new one with a counterfeit signal, maintaining that access, and then collecting and analyzing data, reporting, and recommendations. ISIS and now ISIS-K. They are basically the same thing, except each one is more extreme than the others. Use reconnaissance, messaging, smuggling, logistics reply, hacking, surrender, and current U.S. cyber defenses are inadequate, raising a need for high-level thinking for developing threats. The next slides, this slide and the next one, are not approved by any agency, even though we've passed on our research for 3 years. In fact, the official reports bypass this set of conclusions. However, we've been looking at the South China Seas for quite a while. And the Chinese have used what they call their BKZ-005 medium altitude drone to support both their own and North Korea's threats. In 2017, we saw the possibility of cyber weapons being used to spoof the GPS signals for commercial vessels, ALNIC, MC, and ACX, against our Navy capital ships, the McCain and Fitzgerald. 20 died in this, and I have made it one of my life missions to speak for those 20 dead sailors, that their family should have some peace. I believe that these were spoofed signals, and you do not have to spoof the capital ship. It's protected very well with electromagnetic protections. But I can spoof the commercial vessels. They are legacy operations, and they're very easy to spoof. As captain of a small vessel myself, I know that positioning and the use of collision and avoidance and the AIS systems are so important to knowing where we are and not making a mistake and colliding into somebody. But we tend to be very focused on those GPS positions. We want to know where they are because that's going to estimate where the other vessels are. Same thing in the air. In this case, spoofing the ALNICs or the ACX results in a exchange between the two captains that is very volatile, each one thinking they're on the right mode, and we have a collision. The ALNICs was so big a vessel that when it collided with the capital ship, that it didn't even know it hit them until they came back and recognized they almost sunk them. The destroyers were small compared to these huge tankers. We've also suspected GPS positional spoofs, testing spoofs on the USS Lake Champlain, Antietam, and US Louisiana. So what kind of thing is this a Chinese drone? Well, it has a range of about 1,500 miles, a ceiling of about 26,000 feet, a long endurance, and is like the Predator. It's used for ISR or PLA of China and modified payloads. It has lots of sensors and particularly electro-optical and infrared. What you're looking at here are the Spratly Islands, which we've been following. The red circles you see are intelligence operations and also drone overlaid with drone capabilities. That means inside the circle, that drone can pretty well surveil anything in that area. This is something we put together back in 2017 when those ships were affected, collided, or hurt. And what we have here are the actual ship locations in blue. The reds are Chinese operations. The black is a Chinese intelligence base. And by the way, in the South China Seas, everybody thinks they own it, but the Chinese have a very good presence, and we did too. And these are our operations over here near the East China Sea. Another problem, we are beginning to see the threat, and it has not, thank goodness, come to bear, but it's not something out of the ordinary. This is the radiological dispersion device. And there we have a weapon of mass disruption. The greatest effect from a nuclear incident is fear, because radiation, it cannot be detected by the human senses. You can do all kinds of things with the drone. You can combine it, you can contaminate, you can fear and panic, you get explosive effects, you get conventional expense. Lack of prompt, accurate information available to the public may feed panic. It's a very dangerous possibility. And by the way, conventional explosive radioactive material is available from secondary sources all over the world, hospitals, dentists, so on. So the active goals in the countermeasures side are to incapacitate, destroy the threat in a direct way, like a GTA, or a simple cyber rifle might be working, but not against swarms. GTA efficiency, especially against the UAS reactive, is reduced in urban zones because both the GPS doesn't work and our responses can't work very well. Simultaneous attacks on multiple fronts are very difficult. Some of the countermeasures involve odds, lasers, GTAs of reactions, saturations. We have some passive goals. We have countermeasures that are everything from decoys to sensor jamming and so on. And the aggressor, by the way, is not a dummy either. He turns around using things like swarms with strong collaboration ability to match the swarm locations with combined active and passive measures. Loss of signal, loss of partial false position spoofs. I now want to finish up my presentation using the EICHELBERGER collective detection method. I want you again to recognize that ADS-B and GPS is a subset of a larger receiver localization problem, position fix problem. Solutions that apply to the larger vector space, that is GNSS and GPS, also are valid for ADS-B if the computational hardware is available. GPS, by the way, spoofing is a reasonably researched topic. Many methods propose to detect and mitigate it. The lion's share goes on just detection, but ECD comes out of the brilliant mind of a Dr. Manuel EICHELBERGER, a Swiss scientist from ETZ Zurich, who invented a method for detection, mitigation, and recovery of spoofed GPS signals. Nothing on the market can say that. I gave the name ECD to honor Dr. Manuel EICHELBERGER's work. It is a collective detection process. It is a critical algorithm which detects, mitigates, and recovers spoofing and or jamming attacks on GPS or ADS-B. It is maximum likelihood. It uses snapshot receivers, which is this smaller receivers that are specially designed that take about 1 second of data. It does not determine the arrival times. The angle of attack doesn't matter. Combines all the available satellite and receiver information. That means all 4 or 5 satellites and every single signal, good and bad, and decides only at the end of the computation what to do with it. It exploits the robustness of collective detection and all of its improvements in research. It shows multiple locations, including the actual one can be recovered from scenarios in which several signals are present, including falsified ones. Some of the data behind the ECD shows in TextBat, which is one of the procedures that are one of the testing modes, that it is can allow up to a maximum error of 222 meters. This is less than 1/6 the maximum unnoticed location offset in all others. It doesn't attract signals, as I said. It works with these single snapshots. So there's a reduced latency. 30 seconds latency can be effective, can be a problem. It is aimed at single antenna receivers, however, it can work with multiple. Spoofing algorithms identify all likely localization or position fixes. If you have improved noise tolerance compared to classical receivers, is not susceptible to data modification, and is looking at these things called likelihood distributions, what we were talking about earlier with the worst, best, and normal cases, including the actual ones. Two of the most powerful GPS signal spoofing attacks are the seamless satellite lock takeover and navigation data modification. ECD defeats the powerful and subtle attack on top of the jammed signal. The spoofer sends a set of satellite signals with the adjusted power levels and synchronizes to the authenticated signals. ECD avoids all spoofing and jamming pitfalls and signal selection problems by joining and transferring all the signals into a location likelihood distribution. It works in 4 dimensions. It reduces the computational load by using a fast branch and bound algorithm with SIC dampening, signal dampening. By the way, that it turns out it might be a problem because parts of this are now proprietary. Signal interference cancellation is what it uses after it's picked up all the data. And it removes the strongest and receives signals one by one, hits them with a 60% factor, as a matter of fact, in order to reveal the weaker signals. It's impossible, basically, to differentiate an authentic and a spoof signal a priori. So ECD doesn't remove them. It takes them into the sample data. And that is very powerful. Here's kind of the core of it. Basically, you have 4 satellites, and each one has its first point of a PRN, the pseudo-random number sequence. And when the ECD applies its magic to it, they all are synchronized, at which point then you can start selecting the data because you have a coordinated data, 4 data sets in time, in position, ephemeris data, and everything else. I want you to know that ECD is not the silver bullet. It's better than every solution I've found for position fixes outdoors, that is outdoor localization. But ECD does not compete with other indoor localization methods, the urban canyon problem. ECD prototype has a medium error of about 82 feet. The government can do a lot better, believe it or not, with 55 feet, or in 95% of the cases, but some of their solutions are 10 feet or even less on some of these very specific ones. On the positive spin side, I guess you might call it, ECD works very well for both outdoors and marginally for indoor localization. It has some drawbacks. One is computational load. The other is use of these snapshot receivers, which are specialized. They are not as cheap as classical. It has a part of its response is now branch and bound proprietary because Dr. Eichelberger has figured it out that this works very well, and they're doing a lot of work in Switzerland and other universities on it. It has a huge attack vector space. I mean, this is not something that's simplistic or modern. This goes after spoofing in the difficult cases, and it requires specialized placement of the antennas, and that's not an easy assignment. I have a friend of mine, a colleague of mine, who does this for a living, and I can tell you right now, this is a complex kind of problem. For those of you, I've purposely not done recommendations or conclusions in this presentation because I wanted to leave that open for your thinking, and I can give you some of the thoughts I have in question and answer if you like. But just so that some of the terminology is there, I have 2 slides that are framework definitions, collective detection, localization, navigation data, the course time, and so on, the pseudo-random noise, snapshot receivers, spoofing, and parameters.